So now let's do this lengthy example that I mentioned. Example 4. All right. Now, let C be a mapping from R to R2, so a curve in 2 space defined by C of t is equal to E of t cosine t and E of t sine t. So as you see, this component is a product of 2 functions, and this component is a product of 2 functions. Now, our goal in this problem is to show that the tangent vector to the curve and the position vector, which is the curve itself, position vector C of t, they form a constant angle of pi over 4. A constant angle of pi over 4. Okay, so let's make sure we understand what is this thing is saying. So there's some curve in 2 space, E of t cosine t, E of t sine t, whatever it looks like. Show that the tangent vector to the curve and the position vector C of t form a constant angle. So I'm just going to take, so we just want to make sure we understand what this looks like. So let's just take some piece of the curve. I don't know what the curve looks like. I don't have to know what the curve looks like. That's the power of this. This is algebraic. I'm just using geometry to help me get a grip on the problem. So the position vector is going to be some vector. Let's actually go ahead and draw some. So the position vector is going to be this thing right there. That's C of t. Well, the tangent vector is going to be this thing right here. That's going to be the velocity vector. So as this curve moves, they say that the position vector and the tangent vector, as the curve moves, it always keeps an angle of pi over 4. That the angle between those 2 vectors always stays pi over 4. That's what we have to demonstrate. So what we're going to end up using is, of course, the thing that we know. We know that the angle between 2 vectors is that the dot product of the vectors divided by the norm. We're going to run through that entire algebraic property, and hopefully at the end we end up with what we want, which is this pi over 4 business. So this is just what it means physically. Now we can start doing the algebra based on our rules of differentiation. So this is where the problem gets a little bit long, but there's nothing strange happening here. It's just long. That's all it is. Okay. Well, let's take C of t. So C of t is equal to E of t cosine t and E of t sine t. So I'm going to rewrite that. That's the same as some function E of t. Notice E of t is in both, and I'm going to pull it out of that vector, and I'm going to write it as cosine t and sine t. This is akin to rule number 4. I have some normal function of t times a vector. That's all this is here. I've just rewritten it. I didn't have to, but I just thought I might as well use the rule 4 since I wrote it down. Okay, now let's go ahead and take the c prime of t. Let's go ahead and take the derivative of this. So c prime of t, well, we said that it is going to equal this times the derivative of that plus that times the derivative of this, right? That was rule number 4. If I have a function times a vector, I can just, when I take the derivative of it, it's just a normal standard derivative they always take. 1 times the derivative of the other plus 1 times the derivative of the other. Okay. It is going to be this times the derivative of that. So it's going to be E of t times minus sine t cosine t plus that times the derivative of that. Well, the derivative of E of t is E of t, and that is just cosine t sine t. There you go. So now, when I add these, I can go ahead and actually add them because E of t is in both. It actually becomes E of t, and I'm going to write minus sine t plus cosine t. I'm going to add this component and this component. Now I'm going to add this component and this component. Cosine t plus sine t. That's it. So that's c prime of t. Okay, so now let's go ahead and find the norm of c and t. The norm of ct, because again, we need the norms because let me just write this down. Remember we said the cosine of theta, it's going to equal c dot c prime over the norm of c times the norm of c prime. So now that we have c prime, now we need to calculate the norms. So the norm of c of t, okay, well what is the norm? The norm is the vector dotted with itself, and then you take the square root. So c of t. Okay, so that's going to be this thing. This dotted with itself. Okay, so we're going to end up with e of 2t, right? Because e of t times e of t is e of 2t. This dotted with itself, you're going to end up with cosine squared t, okay, plus e to the 2t sine 2t sine squared t, all under the radical. It's going to equal e to the 2t. The e to the 2t factors out. Cosine squared plus sine squared is 1. So it's going to be that. So it actually just ends up being e to the t. So that is the norm of the vector, the position vector. Okay, so now let's go ahead and do the norm of this thing. So this is going to be a little involved. You just have to sort of keep up with the algebra. It's actually not that bad. So now c prime of t, let's go ahead and calculate the norm of this. So we're going to be calculating the norm of this vector right here. So that's going to equal e of 2t. Okay, I'm going to put a little parentheses here. This dotted with itself, you're going to end up with sine squared t. This times itself is going to be minus 2 sine t cosine t plus cosine squared t, then plus e of 2t times cosine squared t plus 2 sine t cosine t plus sine squared t. And all of that is going to be under the radical. So again, I've taken this vector right here. Let me do it in red. I've taken this vector and I've dotted it with itself. So e to the t times e to the t, that's e to the 2t. Well, this, when you dot something with itself, it's going to be this times this. So this is a binomial. When you do this times itself, you end up with this term. And then when you do this times itself, you end up with this term. But this et distributes over both. That's why it shows up in both places. Okay, so now let's go back to black. We end up with sine squared plus cosine squared is 1. Cosine squared plus sine squared is 1. Minus 2 sine t cosine t plus 2 sine t cosine t. Those cancel. You end up with the following. You end up with e to the 2t times 2 under the radical, and you end up with e to the t radical 2. Okay, so we're almost there. So we have all the components that we need except just one more. Now let's go ahead and move to the next page. So now let's write our definition of the cosine theta. The cosine theta is going to equal c of t dot c prime of t divided by the c of t norm times the c prime of t norm. Okay, that is going to equal, let me come down here so I have a whole lot of room. Okay, when I take C of t and dot it with C prime of t, here is what I end up getting. I get e to the 2t times minus sine t cosine t plus cosine squared t plus e to the 2t sine t cosine t, excuse me, plus sine squared t, all over e to the t times e to the t rad 2. Now, this and this factor out. I have to combine these. This minus sine cosine t plus sine cosine t, they cancel. Cosine squared plus sine squared is 1. You end up with the following. You end up with e to the 2t times 1 over e to the 2t times rad 2. That goes away, and I'm left with 1 over rad 2. Cosine of theta equals 1 over rad 2. Therefore, theta equals pi over 4. So we got what we wanted. We showed that for this particular curve, the vector itself, the position vector, and the tangent vector, the velocity vector, always maintain an angle of pi over 4. And we did this by just utilizing the formula that we know of regarding the dot product, regarding the angle theta between those two vectors, and we just worked with differentiation, and we worked with, that's it. We just worked with differentiation. We just made sure to be very, very slow and easy and to write everything out. So don't let yourself get intimidated by the length of these things. You're going to get, don't feel like you're getting lost in the algebra. Trust yourself, trust the definitions, and just run through the process. You don't have to know where you're going. These problems are too long to know what's exactly happening along the way. But you have to know where you're going to start. So you have to know what it is that you're doing. But if you're sort of wondering where the problem is going, I'm not quite sure, don't stop yourself. Keep going. If you end up with someplace that's wrong, it's not a big deal. You just go back and you start again. Mistakes, that's the nature of mistakes, especially when you have this kind of algebra going on. Okay, thank you for joining us here at Educator.com, and we'll see you next time for some more multivariable calculus. Bye-bye.